Great, thanks, Melissa. First of all, we want to thank Intel for sponsoring the session. Without the sponsorship for the vendors, it makes it very difficult to actually have meetings like this. And this session will be looking at the many changes underway and expected in the future as far as all the different parts of the platform's ecosystem and what's going on in HPC. And it's called The Next 5 Years in HPC, Managing Through Rapid Change. And here are the different panel members. We have Trish, the Vice President and General Manager, High Performance Computing at Intel Corporation. Katie, who's the Hardware and Integration Director, ECP, and the Division Deputy NERSC, Lawrence Berkeley National Laboratory. And Dan, Executive Director, Texas Advanced Computing Center, Associate Vice President for Research at the University of Texas at Austin. Andy, who's the Future HPC and AI Capabilities Lead at Microsoft Azure. David, High Performance Computing Strategy Manager at Royal Dutch Shell. So we have a really tremendous and broad mix of talent here in our panel. What I'd like to ask everyone to please rate your questions in the chat box throughout the session, and they'll be added to the question queue at the end when we have the open Q&A portion. So first we'll start with Trish.
Thanks, Earl. Great to be here, and really, I think this is a great, fascinating topic, just because as we look out, we're starting to see exascale machines coming along, and so what's after that, is what I'm kind of thinking about. But just starting with, I think the big problems, and these have been some of the problems that we've seen for a while, but heterogeneity. We're going to see more and more heterogeneity as we go along, just because more data, more needs to get insight. And then also, how do you program when you have that heterogeneity? And these are going to be some of our big challenges. So let me just jump into some of the things that Intel's doing as part of these challenges, and love a dialogue more about if other people see these as the big challenges and future, where we're going. So Intel, the CPU continues to really be that workhorse that for those most demanding, HPC, modeling, simulation, AI-infused workloads. But as that AI segment has continued to grow, we've seen that growth in the GPU. And there's that need to really diversify and complement that CPU platform. So we have this XPU strategy that's looking at that range of architectures from, and I don't know if you can read the small type down there, but scalar, matrix, vector, and spatial. And so when we really map those into products, we're looking at CPUs, GPUs, accelerators, and FPGAs. And so when I look at where we're going as far as how do we meet the needs of those growing workloads that are coming across in AI, inferencing, training, we're going to probably want some of those specialized architectures. And so that's where we're going to see more growth in that matrix. But we continue to look at the XE, which is really our GPU platform, which will offer, from teraflops through petaflops to exaflops as we go over the next 5 years, and so that we can meet that growing, more general purpose AI and high performance data analytic workloads. And the thing that, and Earl, I learned this from you, in fact, is that growth of the HPC infrastructure, even in the enterprise market. So I think this is going to be another trend we're going to see, where the enterprise market is moving to doing a lot more AI and a lot more high performance data analytics, and their need for high performance computing infrastructure is growing, and we're seeing that density needs, and they're buying actually the infrastructure for their basic enterprise needs. So that's another interesting trend as HPC truly, I think, changes the world, but now is really getting everywhere, in the sense that it's not just in the data centers or the HPC data centers, it's really growing to be in the data centers around the enterprise. So with this growth in heterogeneity, the big challenge, and it's been a challenge as we looked at the exascale era, is programmability. So how do you, with a the diversity of architectures really have a single programming standard that you can use as the framework across all of these different architectures. And so that's where we've been investing in One API. And I think this is one of the most exciting things that we're doing right now as far as the developer environment, because the developers are the ones that are stuck trying to program and really work across all these different architectures. So One API, it's based on unified data parallel C++ libraries. It's got the performance across CPUs, GPUs, and FPGAs. We're looking at making sure it's cross-architecture and cross-vendor, which I think is key. So this is an open standard. We released Gold last December, and it really is to remove those technical burdens and economic burdens of proprietary programming models. And it is a continuing, like we said, we're at 1.0, but it's going to be used for your existing HPC programming, such as OpenMP, Fortran, MPI. It's based on industry standards and open specifications. So it's really what I think we need to get to, is where we can look at a single model for all the different architectures. And I think that's great, and cross-vendor. So my hope is that this will be much more widely distributed, and we can get it so that other people pick it up. And talking about open standard, I think the next big thing with all the data is the need for a faster I/O. So we talk about compute-bound workloads, memory-bound workloads, now I/O-bound workloads with all this data. And so one of the innovations that we've had as part of our exascale program is DAOS, distributed asynchronous object storage. And I'm pretty excited about this. We're seeing that, it's been on the top IOPS list for the last couple of SC and ISC programs. And it's really looking at throughput IOPS with arbitrary size. And so it's an ultra-fine grained IO, or at least looking at software managed redundancy. And I mean, it's exciting, some of the results we're seeing, where we're getting 9x the performance on small access storage and 4 times the bandwidth versus Lustre. And that's with 40% less capacity. This, again, is an open source. It runs on the COT servers with Intel Optane persistent memory. And I think it's just, as we look forward, these are the innovations we need so that we can keep growing the compute and keep growing in this performance. We need that storage to be able to and quickly access the data. We need that programming model that goes across, and then we need those architectures or the actual chips so that we can do the compute we need. So that's what I see for that next 5 years. I mean, we can look beyond that and say, where's quantum? Is neuromorphic going to play in it? And these would be some good questions and dialogue to have. So with that, I'll hand it over to Katie.
Hi, good morning, everyone. So for this little talk today, I'm actually going to have my NERSC hat on. And so if you aren't familiar with the NERSC workload, NERSC is the National Energy Research Scientific Computing Center, and we are a Department of Energy Office of Science supported high-performance computing facility, and we support the mission of the Office of Science. So, and the Office of Science just has a huge variety of workload. And so at NERSC, we have about 7,000 users and 700 different projects. And so one of the things I think we can see kind of early at NERSC is sometimes where these emerging trends are. And so I wanted to talk about really where we see a changing computing landscape and where we see the next 5 really to 10 years. So one thing that others, of course, have talked about is really the explosion of data. From the Office of Science perspective, where do we see it? This data is coming from instruments, it's coming from detectors, it's coming from light sources, genomic sequencers, and sensors. And these communities can no longer analyze their data with a small end station. They are requiring the scale of HPC to do their data analysis. But even more than that, when you ask these scientists, hey, what could you do with this type of computing power? It opens up a whole new realm of possibilities. And scientists start to talk about, well, actually, if I could get feedback to my experiment in a matter of minutes, that could help me steer my experiment. It could help me decide the next run to do. And so what we're seeing emerge is the need for kind of a real-time ability to drive and provide feedback to experiments with large-scale simulations and modeling. Okay, so that's sort of the graphic on the left. If you go to the right, of course, there's new methods for AI that we see not only being incorporated into data analysis, but into simulations as well. And so we see the confluence of those two needing to be supported on HPC systems. And then finally, when you take the technology perspective into account, we have increased heterogeneity, as Trish mentioned, and the need to be able to program those distinct elements in a way that's useful for users. So let me just animate this slide here, Earl. So what we see these communities doing today is really unnaturally trying to map their workflows, these complex workflows, into existing HPC systems. And they can do it, okay? There's no doubt these scientists can figure out a way to use HPC systems, but it certainly isn't easy. It takes custom solutions, and it's really challenging, and it's not necessarily reusable for the next community. And so I think where we're going to be going in the next 5 years, as we see these new science use cases emerge that really require HPC capabilities, we're going to see an increase of, we need to have more programmable systems. We need to have composable systems so that we're able to map these complex and different workloads a lot more easily onto HPC systems. And I think then the focus is also going to become, when we're talking about the performance of a system, it's not going to be the performance of an app, okay? It's going to become the performance of this end-to-end workflow. How can you get your workflow done? And so we're really talking about programming much beyond the HPC system. We're talking about including our storage systems, our networks, going out to the edge towards these instruments and detectors. It's programming the whole facility that's going to be important in the next 5 to 10 years. So with that, I'm happy to take any questions too. Or no, we're going to do questions afterwards. So I'm going to pass it over to Dan.
Thank you very much, Katie, and thanks, Earl, and everyone else. And just go ahead one slide so we see some text here. One build in. There we go. So, so we were asked to make predictions about 5 years, and knowing Trish and Katie would fill in much of the technology landscape that is coming. The thing I want to stress is that, whenever you predict rapid change in 5 years, you're almost inevitably wrong. We've been talking about, implementing thread level parallelism with OpenMP and task level parallelism with MPI. We're in year 26 of that conversation, and it's not over yet. So, one theme here, I think, for the next 5 years is that the more things change, the more they stay the same. So we are seeing rapid technological change after a sort of somewhat level period with sort of two options in architectures. But I think the conversations will stay the same. So if you think 5 years out, clearly we're going to have more heterogeneity in the types of silicon that we have options to deploy. We'll still be fighting over how to deal with that and managing the heterogeneity in 5 years. It's just not something that's going to go away. We have many good options on the horizon for, converging programming models. The problem with having many options is we don't have one. And so we still probably won't have a single programming language 5 years from now. We will have, likely more object stores, and the nature of storage is going to change some, but that the applications are going to want a POSIX interface is also something that's not going to go away in the next 5 years. We will certainly see more containerization in the HPC space. I expect most jobs will be containerized within 5 years. And that will still not solve our problem of being able to manage software effectively. We'll do a horrible job of that going on. So I think storage will likely be mostly solid state, and we'll start to treat disks like we treat the archive tier today. I don't think disks will be gone, but I think your reads and writes from your applications will primarily go to solid state, 95% of the time, and then, copy off to disk somewhat later. We will have HPC and AI workloads that will be mostly indistinguishable. And this is something that I think will be easier for the HPC folks to deal with in the clouds. So once they are large scale and model parallel in AI, they're going to have all the characteristics of an HPC workload, including having massive I/O problems for many of them. So, we'll talk about them in one bin, but we'll have the same set of problems there. And as Trish mentioned, and Katie mentioned with data users, the sort of things that we consider HPC workloads will be even more pervasive than they are now and sort of everywhere. However, we will have some problems to deal with. So if we could do the next build in here. So I think if you could pop that up. So I think there's still going to be one problem that we're going to start to see more and more of the consequences of in the next 5 years. And that is the fork between what I'll call the exascale crowd and everyone else, by which I mean the relatively small number of sophisticated users that we have who are really pushing the envelope of how we exploit hardware. If you could do the next build in. So the sort of top fork there in the HPC workload, we've already heard some of these words and how people are dealing with applications today, are ready to embrace heterogeneous architectures, who use Cocos or Raja style C++ templates to do their applications, who embrace directives, who do collective offloads in the programmable networks, who have HDF5 to manage their I/O, who address parallelism effectively at the instruction level, at the thread level, at the socket level, at the node level, who are used to dealing with these very deep memory and storage hierarchies and build incredible and amazing applications that get great performance. And that'll be about 20% of our workload. And at the other 80%, we have a different trend. If we could hit the last build in, and they just do Python. And the long and the short of it is they don't even want to hear about most of these other topics. If you have heterogeneous hardware, if you want to add GPUs and CPUs or TPUs or, ARMs with high bandwidth memory or whatever it is, that's fine as long as my Python notebook executes on it and executes well. And so, just the explanation I went through for the top box would cause most of them to run screaming for the exits. So I think, even worse, they not only want Python, they want Python in a notebook that runs interactively at, the petascale, so, and beyond. So I think in our application and user base, we see this divergence more and more between the sort of very sophisticated users and the much, much more numerous, less sophisticated users who want to do something but who still have, computations that scale beyond the server under the desk type model. So how we deal with that fork, I think, is going to be our central challenge because, frankly, we deal with changing architectures and programming models and I/O systems all the time, and we'll just complain in the same ways about the new ones as we did about the old ones in the years to come. So that's my 5-minute spiel on where we'll be in 5 years, and I think I am handing off to Andrew Jones. So, Andy, take it away.
Thank you, Dan. So as I was thinking about the next 5 years and the challenges and trends that will emerge in the HPC community, I came up with 6 threads. I could happily talk about each of these 6 threads for a long time, and indeed some of them I am actually giving additional presentations on other conferences in the next few months. But the first one, really, I think Dan has already covered that pretty well. 5 years' time, we're still going to be debating programming languages for all the reasons of technology diversity and changing in user expectations and so on. Interestingly, I think in 5 years' time, we will no longer be debating cloud versus on-premises computing. Not to say that either of those is going away or either of those will emerge as the undisputed winner or anything. I think they'll both just become a normal part of our conversation of doing HPC. In the same way that when GPUs were early on the scene, there was a big debate about really what was their role in HPC? Did they really have a role? And now, of course, we just accept that GPUs are one of those options for the technology solutions of HPC. Sometimes CPUs are best, sometimes GPUs are best, etc. And I think that is where cloud is going to end up going in 5 years' time. It's going to be accepted as one of those technology solutions. It'll be brilliant for some situations. It won't work for other situations. So as I said, it'll become a non-debate, and the comment there from my point of view within a cloud company, I'm essentially just building out supercomputing centers, and then obviously that becomes a cloud for somebody else. 5 years is a long time in technology terms. I think we're overdue some new technology emerging that's perhaps slightly unexpected. I think in 5 years' time, we will be evaluating actively as a community, evaluating a new technology for high performance computing. In the same way that GPUs emerged a few years ago and so on. The photo on that slide is actually of a quantum computer, but I don't think it will be quantum computing that is the technology that's keeping us occupied and having us all evaluate stuff in a few years' time. I don't know what that technology is now, and I think that's the point. I think 5 years is long enough for something to emerge that we haven't really predicted yet, that will potentially soak up a lot of time figuring out and add more into that diversity of technology that the previous panelists have already talked about. I think one of the other things that is definitely going to be a trend that has already started in the community over the last few years and is gathering pace is the changing nature of what it means to be HPC. So this idea of driving new pressures on how we implement HPC and how people want to use HPC. Some of that comes from new user communities, both completely new user communities to using high-end computing or using them in different ways, such as Casey was discussing, or new communities within companies, so perhaps moving away from the traditional science communities within an organization to maybe more of the AI or machine learning type workloads within a company wanting to use the HPC infrastructure. I think another axis along that is, and Dan touched on this, is those new users and a lot of the old user communities have an increasing expectation around ease of use and ease of access to the facilities. And the willingness to take pain or to put effort and finance into achieving performance does not, to me, to be as strong as it was in the early days of supercomputing. There's a much greater emphasis on user productivity. I think the other trend that's coming through from the business pressures is a greater emphasis on the maturity and the professionalism of HPC services. So things like business metrics and so on, building out service structures, not just deploying hardware and so on. I think that's going to become more and more prevalent in the HPC world. And then, as I said, that trend has already started. Unfortunately, in 5 years' time, I think we will still be addressing diversity and inclusivity challenges. HPC is very much a world of people, and this came up in a conversation somewhere in another forum recently. It is still an environment that is driven by individuals and is driven by people. Because of the challenges we have to overcome, it takes people to drive through those challenges and make it happen. We've made a lot of progress as a community in raising awareness around the diversity and inclusivity challenges and trying to improve that. But I think actual progress in fixing that has been not as much as we might hope. And sadly, I think in 5 years' time, that's still where we're going to be. Hopefully, we will have made big progress, but I think there'll still be a long way to go. Having said that, I still think in 5 years' time, we're going to enjoy working in HPC. It is one of those areas that touches on technology challenges, people challenges, and organizational challenges, and large scales. A lot of people get into HPC by accident. Very few people I'm aware of actively choose to leave HPC. And I think that is still going to be true in 5 years' time. It's still going to be an area and discipline that will be extremely interesting to work in, and people will enjoy working in that. So kind of those are my 6 themes, and we can take more questions about them at the end. But I'll hand over to David now for his thoughts.
Okay, thanks, Andy. I think one of the advantages, or maybe the dangers of going fifth in the line, is I think I'm going to be agreeing a lot with my the other panelists. So, but let me talk a little bit about what we see for HPC inside Shell as we go from this, being an oil and gas focused company to an energy focused company. I'm sure people have seen Shell's and other people's announcements about what we want to do as we do this transition, in Shell's case, out to 2050. So I'm sure most people are aware that a lot of what we do in HPC inside Shell currently is with seismic exploration. This dominates our workloads. But what we're seeing, and Dan kind of touched on this a bit as well, was we're seeing a lot more other applications coming onto our systems that are not seismic. Some traditional HPC applications, you can think of fluid dynamics and modeling and AI, and a few which I think will be new to the segment as we go forward, particularly as we change to look at lots of different technologies. We'll still do things like computational chemistry, but I don't think seismic exploration actually shrinks per se. I think we will always want to be trying to get that better image, trying to get that clearer, path to the resources. But I think it will become a smaller part of the pie. And one of the challenges I think we will see as we look to build out HPC inside a company like Shell is we will have a lot more users and applications. I don't think I will have as many as Katie. Or at least I hope I don't have as many as Katie, but I think we will be going from hundreds to thousands. There are 80,000 people in Shell. I don't think everybody will want to use HPC, but I think a surprising number of people will be using HPC somehow. Dan talked about Python in notebooks, and we see a lot of that, and people want to do HPC-like things. So HPC stays a key enabler. I think we have an incredibly important part to see to really help the energy transition. I don't think that will ever go away. I didn't put it on here, and a few other people mentioned it. Writing good algorithms will be our number one job. I think it always will be. It doesn't matter how we change the HPC market. I think if you can't write a good algorithm, then you're not really going to make the most of what you've got. I like to talk about storage quite a bit. I think we will get to an exabyte before we get to an exaflop. I'm closer to an exabyte now than I am to an exaflop. I don't think that will change. I think this is one of the biggest sort of hidden problems we have. And I think as we get more mixed workloads, this will just become harder and harder. We already struggle to move data around efficiently. Trish talked about the sort of challenges there, and the sort of the end-to-end performance as well is very critical, as Katie mentioned that. Just how do we feed the beast? It's not simple. I think we will also be entering a very diverse marketplace. It's definitely changed. There's a few comments in the chat window at the moment about FPGAs and RISC. Yes, I think they're all part of the mix as well. I don't know how we do that yet, but this idea that we have a very diverse marketplace is going to continue to challenge us, and how we choose the best technologies and how we stay on the cutting edge will be difficult. I threw quantum in here. If you, Detlef Hole, who's our Shell's chief scientist, is on one of the recorded panels talking about Shell's view of quantum. I think it's a software problem more than a hardware problem, but we will still have to work it out. And maybe Andy's right. Maybe it isn't quantum. Maybe it's something else we don't know yet. Power, cooling, networks, storage, memory. I don't think any of these things change. So I think those are kind of the three things I was sort of thinking about as I came into this for the next 5 years. So maybe Earl, back to you for the panel.
Great, thank you very much. And for all the panelists, I'd like to start with one topic that was brought up by a number of the presenters. In particular, Andy, you brought it up directly as far as the talent issue. Trish, you mentioned it too. And David, you mentioned the issue about writing algorithms is kind of the number one issue, requirement, or however you want to phrase it, for success. And so the issue I'd like to ask the panelists to address is how we're going to address the talent issue. One of the issues in HPC is a lot of the folks who the expert programmers' expertise are aging out and retiring, and we haven't seen that new set of people join, the community, so to speak. And part of the issue there, I'll put a little of my opinions in here, but Andy addressed it directly too, is I think one of those parts is we have to engage and get more support and interest in the younger community, in particular in more diverse communities. And also, how can we move HPC, science and technology, to kind of the disenfranchised parts of the world and communities out there? And all under the umbrella of creating a larger pool of IT talent, HPC expertise, which is obviously required for growth. So what I'd like to ask is, do you have any ideas, suggestions? Andy, you mentioned that you hope that things get better within 5 years. I share your belief. I really hope it does, but this is a long-term problem that's going to take a long time to solve. So I don't know if anyone wants to start with comments or suggestions or ideas.
I'll start, because I mean, this is something that even when I was at Lawrence Livermore, we struggled with trying to bring people in and keep them focused in HPC. I do agree, Andy. Once you start, you get sucked in, but it's not something that's readily available. So I love the way that the conferences are doing a lot of the student competitions. So Dan Olds, I know we're working with him. He's putting together a winter cluster challenge really focused on HBCUs, which I think is wonderful, bringing it to a wider community. But I think the conferences, we need to really lean in more and more with the student cluster challenges, just the internships and those kind of things. And when I was the chair for SC, one of my big focuses is why I did HPC Matters was to get it also to make it cool again to be part of HPC. It was kind of my goal, right? And to get even Congress and some of the governments more excited about the power. Now, Exascale is kind of taken over, and so there's a lot more funding there. But I agree, we still need to bring along the new hires so that we keep the pipeline full.
Yeah, I'd just add, I think there's a ton of young talent out there, but the trick is getting it to work in the areas we want them to work in our field, and have Andy stop hiring them all to go to Microsoft instead of at the HPC centers. But part of that appeal is how we characterize it, and we found we get much greater success when we talk more about the application domains and why it's impactful than saying don't you want to play with big computers. So not that I really have any understanding about how anybody would not be excited about wanting to play with big computers, but we have our Computing for Social Change initiative, and we find that if we focus on social justice issues, environmental issues, all of which are AI, big data, have massive computational needs. It's a lot easier to take somebody who's passionate about an application and teach them Python than take somebody who's passionate about Python and teach them an application area. So so the way we package it, I think will broaden the appeal of what is not strictly HPC anymore. Will bring a much more diverse workforce to us in the future.
I mean, we also need to listen to what the younger scientists and the younger generation are trying to bring to supercomputers. So when we get postdocs in at Berkeley Lab, they want to run their Jupyter notebook, they want to do it at scale. We should make that possible. Actually, we have to make that possible in order to support these new kinds of use cases that are coming up. There's a real competition for talent, and so recruiting people to do Fortran, I don't think is going to cut it. We're going to have to enable these capabilities and make our systems more flexible and dynamic in order to attract the talent that we want in our area.
Yeah, I want to echo that point that Katie's just made. I think the people coming through, either the younger generations or coming in from other areas into HPC, have not necessarily grown up the way maybe we all have with this is how HPC is done. And I think we need to recognize that that's a richness coming in, bringing those different perspectives and maybe moving our field on from the way it's been done for the last few decades. I think the other comment I'd like to make is that in some respects with the question, Earl, you kind of entwined two things. One is how do we grow the talent pool for the future? How do we solve the engineering challenges we have? And that overlaps with, but it's not quite the same thing as how we address our diversity and inclusivity problem. Because even if we weren't to change the scale of the workforce, we can bring in lots more people in. I think the other aspect of the diversity is it brings different perspectives, and a diverse team is generally regarded to be a more productive and a more capable team overall. So I think there's kind of two axes there, and it's not just about getting more people in the door, although clearly that is a strong driver as well.
And I think we have to recognize a little bit when we bring people in that it takes a long time to get very good at HPC. We really, as a company, we need to invest in people and really take that time to grow them and their career. I think that's very important in attracting the talent and also retaining it.
Great. And the next question I'd like to do is combine a couple questions we've gotten already in the chat window. And it's basically around some specific new technologies. Andy, you mentioned that you felt that there would be a new one that hits real strong within the next 5 years, but probably not quantum. But the questions we've received, I think 4 questions now, are related to FPGAs and RISC-V. And the questions are basically, do you think they'll take hold more so than they have in the past? On the FPGAs, they've been around for a long time. They've had a certain footprint, some good success in finance and certain application areas, but really haven't taken on. So the question is, do you think any of these specific, meaning FPGAs and RISC-V, have a chance to really take hold and become a major player in the market? And if not, or if so, what's holding it back? What's causing them not to become as popular or as strong as they could be?
I think both of those will be non-trivial players in the market in 5 years' time. I don't think either of them will be major players in the HPC market. 5 years in HPC, in some respects, is a long time. In other respects, is not a long time. And as an industry, we don't actually move that quickly to new technologies.
So I would say that with the growth of edge, I wonder if FPGAs will have more opportunity as we, as Katie talked about, all the experimental facilities, what we're going to do there. So I do think there is an opportunity for some growth. Obviously, the programming is the challenge there. And I agree with RISC-V. I think it would be, it takes time to develop the ecosystem in HPC. And so, but I do think we'll see more RISC-V. But
I think from my perspective, FPGA's programmability has been the issue since day one. And, edge devices tend to be more special purpose and it could do better there. But, will we see a wave of SYCL applications that can finally directly compile the FPGAs and take off? That involves both that working and, people adopting things like SYCL to program them or other technologies. I still see FPGAs as more of I have a handful of applications I need to optimize. Not I have a million applications that I need to optimize. As a target, RISC-V, there is, I'm more sanguine about sort of proliferation of architectures like ARM and things like that in the HPC space. You at some point you have to make some ruthless decisions in an architecture ecosystem, and I'm not sure RISC-V has done that in every edge condition that it needs to. We'll see. I'd love to see it be successful, but I'm not convinced yet.
David or Katie, do you have any view as far as on FPGAs or RISC-V?
It's fairly similar to Dan's. We continue to evaluate them at NERSC, and on our central system, we want it to be able to be usable by many users. And so the question is that the right place? Is there a better place actually on the edge? And the same comments on the programmability is still quite challenging for users.
Yeah, I agree with Dan's comments. But we talked about heterogeneity in most of our talks before this, and maybe that's an opportunity. If HPC becomes more heterogeneous, then maybe FPGA and RISC can, ride that wave a little bit. So I think opportunity, but programmability is going to always be the problem.
Right. So the next question I would like to ask, and Dan, you had this in your slide, and that was really the split, and you showed a very definitive split that you feel the world is going to split into 2 categories, groups, or whatever you want to call it, and that's the very high-end exascale systems, buyers, users, and then everyone else. And last December, we had the installation in Japan at RIKEN, the Fugaku system, which is the first $1 billion supercomputer. So when you talk about different classes of performance, it's also seriously different classes of, budgets and spending money. What do you think will be the main difference between those 2 categories you had there? You mentioned, for example, programming in Python. from my view, I would add most traditional modeling simulation, most of the applications are actually going to be falling in that lower tier that you had also. But for maybe Dan first and the rest is just, does everyone agree that there's going to be a split in the market? And secondly, how would you describe that difference between the two categories?
So, yeah, I mean, that was a little bit of an oversimplification, but I think we already see, a pretty big divergence in our application base between the sort of people, who have a problem that no longer fits in the way that they used to do things, and now, need 10, 20, 30 nodes or 50, 60 GPUs to train a model, versus, and I mean, I see this whenever we have conversations with users. We had one just a few weeks ago, people on Frontera, and, you have the people whose efforts in software are 30 or 40 FTEs to move an application forward. And, we talk to them about their teams and they're like, well, we have a dozen FTE on this particular library to fix it. And then you talk to somebody else and it's like, yeah, I have a grad student and I work on this about 6 hours a week. And we make these incremental modifications to our code. And there's way more of the latter group than the former. The former uses a lot more cycles and sort of dominates the system. So, but I mean, you can just look at job sizes. There's a lot of things in the sort of rack scale level problems. And I think there are more of them and they're harder to enable because they're not as open to, eagerly swallowing the next new technology that comes down. They're like, what's the minimum amount that I have to do to perturb what I'm doing now? So, I think that split's already there and it's just how we continue to enable them and, try and get both groups to run on our systems. So.
Yeah, I'm not sure whether it'll be a hard bifurcation between just the exascale group and just the everybody else group. I think it's a spectrum really, but what we're seeing is that spectrum widening and significant differences between the ends of the spectrum. I think that's probably a fair statement. There will be people from that everybody else label you had who are willing to take a little bit more pain, a little bit more effort to get a performance level, but not as much as the exascale group. And likewise, there will be users of the exascale systems who want to back off on extreme effort and just make what use they can of the systems, not necessarily the most extreme use of the systems are. So I see a spectrum rather than a hard bifurcation.
Well, I agree with you. Go ahead, Katie.
I was going to say, let's get a little disagreement here. I mean, so I think that that split has always been there. From my time at NERSC, we've always had very high-end users using huge percentages of the system, and then many users running kind of smaller jobs. But it's those users that are kind of pushing the envelope that kind of help us drive the technology. And also, you see the technologies that are developed on the exascale systems or part of the Path Forward programs. These become the commodity components in a generation or two. And so I think it's all part of the path. What I do think is new, and probably where I agree with Dan, is that we now have new communities coming to HPC that have never used these systems before. And so their expectations are a little different, but I think we have to embrace them and show them that these big systems can be used for more than astrophysics and climate models. They can be used for biological applications, for light source applications, and some of these new communities that maybe haven't grown up in the world of Fortran per se.
And I think for some of that, we need to, as an operator of HPC inside Shell, we need to look more like the cloud does to people who are used to using the cloud. I just want to run my application and I want to get out and I don't want to spend a lot of time worrying about having a Linux account or whatever it is I need or whatever hurdles I need to jump over. So, but the users who have an Excel spreadsheet which blows up their laptop every time they try and update a cell, we have to cater for those people as well to just make it simple.
Yeah, I was just going to say, I mean, this has always been a challenge. So I don't think it's new. There's been those both extremes. And I agree with Katie that the technology has flowed down to help. But I do think we still have a challenge of making HPC easier to use. And it's always been this way. There's always been, and it will help with our bringing in new people too, if we can. But I see the workstation users are now migrating up. And so I do think it's a growing group. And so it behooves us to look at how to make it easier to use so that we can take advantage. And I wonder if the cloud service providers will help us there, because that's going to be one of their biggest challenges, is making it easy for people to move to the cloud. And so there might be an opportunity for that easy use.
Great. So perhaps we can elaborate on that. We've gotten a few questions related to the issue. Everyone's brought up that there's going to be more diversity in hardware, complexity in the systems and everything else. And Trish, you and a few other people have mentioned how important it is to have or portability between hardware and the ability to move your code and run it in multiple places. Well, if you take those two trends together, it really makes the programming, the redesigning your applications and everything else much more difficult. And many of you have mentioned pieces of that, but could you expand or elaborate on some ideas, or perhaps from a user perspective, what can users do to try to, move things forward with their applications?
Well, one thing we tell our users, and I know we have vendors on the call, is not to program in a proprietary language. That's going to help you. You want to be in an open standard because these systems change quickly. You may get allocations on different systems at different facilities, and it's going to only behoove you to be able to move, and not using proprietary programming language gets you part of the way there.
Yeah, I mean, I agree with that. Coming from, a national lab background, I've always been a big fan of open source, and so the open standards, I think, is key. And a lot of the work that the new technology, even through the Department of Energy, is funded to do open source. So, do you think that's a good trend?
Yeah, I think there's a number of different standard solutions or software technology solutions that can help smooth the path a little bit, but at least for the next 5 years, I don't see anything beyond collaborating with teams of people who do understand the technology and do understand the software and do understand the portability issues. So, whether you call it the research software engineering person, that's kind of a label that's grown up, whether you call it collaborating with your favorite supercomputer center, whatever it is, I think that is still by far and away the most powerful thing that users and computational scientists can do to deal with these technology problems and technology opportunities. Yeah,
I'd echo the collaboration is key there. I think it's incumbent upon us as HPC providers to sort of move towards where the users are in terms of programming models, right? I mean, I see lots of comments around, if betting on C++ is not a way to add more people, but in the chat there, but and I pretty much agree. But at the same time, I think users need to somewhat help us adapt and understand that there might be some effort to move your work into an HPC environment, and that if you really want to get good performance, putting some effort into that is helpful. I think the number one thing you can do is not necessarily choice of language, but use libraries, right? I mean, anytime you can build a good abstraction that allows us to improve performance under the covers, right? If we have a deeply optimized, BLOS or FFT or whatever the algorithm is, turns out for AI, it's those same ones, but you can call that from Python or wherever you want and still get good performance. So I think libraries is one of the things you can do to meet us halfway, and just accept that you can still have a Python notebook, but we might ask you to write it in particular ways.
Yeah, and I think we have to keep trying to optimize for code. That's going to be the tricky bit. It would be wonderful if we had one code which did everything beautifully, but that's not how it works. So I think picking and choosing a little bit is important, but like Katie says, don't back yourself into a corner which you can't get out of in a few years. So.
Excellent. So then the next question I'd like to cover that has come up in the chat, and again, Dan, you actually had that in your slide too, and that's the whole issue, the evolution between HPC and AI. In a lot of our surveys, we're seeing that AI is being incorporated in traditional modeling and simulation applications at a fairly high rate. But one of the questions is, do you really see this convergence between the two so that they look almost the same, as you were mentioning, Dan? Or are they going to require different types of developers, different types of infrastructure, and kind of go down two different paths? Or do you see that they actually will look very similar? And I could even add a third path, and this is kind of for Andy, is maybe one path is a cloud path that might have a different set of developers, tools, and solutions also. But so the question is really, do you see it merging together or going separately? And do we need different types of developers and infrastructure to address HPC versus AI/modeling, machine learning, deep learning?
From an infrastructure perspective, I really hope they go the same path. It'd be much easier for us to support them than separate systems. And I see no reason they can't, right? The core of deep learning models is doing little 4x4 matrix multiplies most of the time, right? Which is what we built HPC to do in the first place. I think what we're likely to see is, very similar things with drastically different terminology and naming, right? Because there seems to be an obsession with reinventing all these things, which we've seen, data science and Hadoop and various other things. But the multi-billion parameter, really large AI models, GPT-3 and other things that are coming along, require model parallelism, which means they're going to inevitably end up using interconnection networks to move data back and forth. There's only so many ways to move bytes of data across a network. They're going to have something that looks a lot like MPI, but is called some AI transport library that is coming. But, I don't see why the hardware can't be the same under the hood for those when all is said and done. I mean, I/O patterns are a little different, but, it's not like we have one HPC I/O pattern to begin with. So I hope the infrastructure converges. The language and the tools may not. But they will end up doing relatively similar things. And then, as you said, there's a lot of blending of these techniques into the traditional simulation code, so they're probably going to be indistinguishable in a few years anyway.
Yeah, I wholeheartedly believe the infrastructure is the same. And I think the biggest challenge I find, at least at Intel, is that HPC is not viewed right now as being the infrastructure for AI, and it's helping people understand that we have the same challenges fundamentally. But I agree the terminology is probably what's going to trip us up the most.
Yeah, I mean, if you look at the first HPC systems that had GPUs, I mean, AI wasn't really a factor in determining kind of that technology. Then the deep learning resolution came along, and we had these big GPU systems that I think are now being used for AI as well. I think where you might see some changes is a lot of times our HPC systems were optimized for I/O writes. How quickly can you write data out of the system? And I think we're already seeing kind of a rebalancing of reads and the need to be able to ingest data quickly for I/O models. I mean, at NERSC, we're already seeing scientists who have simulation codes that are replacing part of that simulation code with an AI model. And it's going to happen slowly. I mean, these codes need to be validated. Papers need to be published. This doesn't happen, overnight, but it's definitely happening in the NERSC workload.
Yeah, and I think HPC has always been a very broad church. We'll welcome anybody. And I think with AI in a few years, AI will be hitting all the problems we've always hit about, I/O and CPUs and choices that we have to make around different things. So I think I'm a bit more optimistic than Dan. I think AI will just be an HPC workload. I think it already is. I think, and we will just embrace it like we embrace all the other codes we've had to do over the years.
So I'm going to play my spectrum answer again, and that there absolutely are use cases where it makes sense to design and build an infrastructure that is purely targeted towards AI workloads to get the best performance, the best economics for that. Likewise, there is definitely use cases where it makes sense to deploy an architecture focused towards specific types of traditional scientific computing, seismic imaging being the obvious example. But there will be a lot of places in the middle that try and have an infrastructure that is capable of both, partly to solve the the manageable infrastructure problem that Dan was talking about, and then partly obviously to solve the integration of the workflow problem that Katie was talking about, where you bring in machine learning and traditional modeling together. So I don't think it's going to be quite as simple as one size fits all. It's going to be that spectrum. And the trick is finding which parts of the infrastructure are sufficiently common. Maybe that's a data center level. Maybe it's not even the data center. Maybe there's different data center requirements between them. But there will be a use case for AI-specific capabilities and HPC-specific capabilities. But to be honest, that's about the only thing that the cloud is really bringing to the table, is that we can afford to deploy all of those at scale and let people choose. Other than that, the cloud hasn't got any magic that big HPC centers don't have in that respect, other than we have multiple of.
I think that's part of the challenge for HPC centers is like how many of each of these components to make to build up your system, and then how can they be programmable and flexible for your own workload, which can be very different across these facilities.
Great. So I think we have time for one more question. I've got a couple versions of this, and it's related to cloud computing. Andy, there's been some fascinating news in the last few days about a major weather site actually deciding to use your solution for a weather code, which is traditionally a fairly hard code to scale and parallelize and so on. And the real question is, can everyone speak to the future portability possibilities between on-prem and the cloud?
So I don't know. Even portability is hard there, but but sure, a lot about the sort of bursting hybrid, and I think it ignores the challenge of moving data around. If you have very big data sets, then trivially moving between systems is really pretty hard. And there are some really well containerized workflows that aren't particularly data intensive, that are awfully easy to move around, in the sort of high throughput space. The Open Science Grid is a great example of that. Workload for the Large Hadron Collider and all those similar types of things where you can easily divide it into little packets. But there are a lot of applications that don't necessarily fit into that. And I mean, if you do what you should be doing and, adopting some of the really great APIs on the clouds out there for doing functionality, or even in HPC centers, those don't necessarily work between systems. So, the provisioning is different, the acquiring resources is different. I think, again, there will be some instances where we're really good at that, but there are others where it's going to have a lot of friction for a long time, I think. Mm-hmm.
Well, I do question the economics still, because in the HPC centers, they're so fully utilized that people are bursting to the cloud because they need those extra cycles. And there's definitely workloads that are fine for the cloud and have been in the cloud for a while, such as genomics and some of the other work. So I can see the growth in the cloud just because the insatiable desire for compute, and I think the cloud is getting much more capable. But I agree with Dan, the data movement, and then also the economics. People are going to have to face those challenges, but the cloud is definitely growing in the HPC space.
Yeah, I think just to touch on Trish's point there about the economics, what we sometimes forget is that the supercomputer community has not been a community driven purely by performance. It's been a community that has spent decades learning how to extract every bit of performance out of a given dollar. And I think that's really what defines the supercomputer community. So that they are really, really savvy about performance optimization against cost and against budget. So that is an economic challenge for the cloud organizations to deal with, as you are coming up against the most cost-efficient customer base, essentially. In terms of porting between clouds, my argument that I've been talking about for a number of years now, it's not just a new thing, is that it's no different, as Dan said, to porting between working at one national lab and then taking your workload across to another national lab, or indeed when you buy one supercomputer at a center and then you get a completely new supercomputer in a couple of years' time, and you've got to migrate all of your users and your workloads and your applications across, particularly if there's a big technology change. NERSC will be the obvious example, going from KNLs to GPUs, for example. So there's nothing special or magic or different about cloud providers in that respect. It's just moving from one big system to another is always difficult.
Yeah, I get tripped up by this question because for a long time I've thought of NERSC as just a science cloud, right? We run a huge supercomputer and it's optimized for science applications. So that's what our staff have in mind. That's what our staff are experts at. And so we're just this focused area. And there is a business model challenge too. I mean, our users get an allocation a certain way. And so then how are they going to surge to other places? But I will mention, we often talk about, there's a couple of Office of Science HPC facilities, the Oak Ridge Leadership Computing Facility and Argonne Leadership Computing Facility. And so what we have started to do is think about how we can surge between each other if there's like a maintenance or a facility issue. And there's a light source that has a big experiment. How can we provide the ability for those scientists to be able to run across our facilities? And I mean, it's not even at 3 HPC centers, it's not simple to go from one system to another.
Yeah, especially if those HPC centers are themselves on slightly different business models, like between NSF and DOE, for example, and stuff like that.
Right.
Right. Yep. And with that, I think we're out of time for the panelists. So I would like to thank all the panel members for joining us, and also for all the attendees. If you missed any earlier sessions, you can select the Past Content button on the top right hand of the screen under the Schedule tab to see recorded presentations from earlier in the conference. So at this time, there will be a 1 hour break. The next session is starting at 1:05 p.m. Central Time. And you're welcome to network in the lunch break room by clicking on the tab on the left side. So once again, I'd like to thank our panel members for an exciting and enjoyable panel. Thank you very much.
Thanks.
Earl.
Thank you. Bye.